Hi, my name is Natalie Harold. I'm a prosthetics resident here at the University of Michigan Orthotics and Prosthetics Center. I first got introduced into the field of prosthetics through my undergraduate degree, which was in mechanical engineering. So one of my first projects I did was in prosthetics, and that's when I just got hooked. I found a way to apply technology and engineering to healthcare, which were two avenues that I was really interested in, so it seemed like a perfect fit for me. So this is an example of a prosthesis for someone with a below-the-knee amputation, also called a transtibial amputation. This top part up here is called the socket, and this is the part that the patient's limb will actually fit into. It takes a lot of time and appointments to get the fit of this socket just right, and it's, I would argue, the most important part of the prosthesis, because if it doesn't fit comfortably, the patient just isn't going to wear it. Just below the socket is an elevated vacuum system. So this is what's considered probably one of the most advanced components in prosthetics today. This elevated vacuum pump works by just pushing the button here, and you can hear it turn on and start sucking air out of the socket. Below this we have what's called a pylon, and that's basically a way to connect and to align the prosthesis and get it to be the right height. A lot of the components that we select are based on patient's activity level, but they're also based on patient's weight. So these components here are made of aluminum, the pylon and tube clamps and such. They're weighted to 250, 300 pounds typically, and those are the ones made of aluminum. If we have patients that are heavier weight than 250 pounds, which we often do, we'll have to use heavier rated components made of titanium or stainless steel. Some of those can be weight rated up to 500 pounds. And then we have the prosthetic foot. So the foot is mostly covered by a foot shell, and this part just allows it to fit into a shoe properly. So this is kind of an iteration of how we create a prosthesis. The socket starts with a cast of the patient's leg. So we'll take plaster, just like a cast if you were to break your leg, and we'll wrap that around the residual limb to create a negative mold of what that limb looks like. Another method that we use, which is much cleaner, is using a white light scanner. And we use the scanner to take the mold, and then we can modify it on the computer. And then this next step here is called a test socket. And this is the very first type of socket that will fit on a patient. It's made out of PETG plastic, like pop bottle plastic. It's also really easy to modify, so we can grind out the inside of it, we can heat it up with a blowtorch and push and stretch the plastic in any way that we need it to. At this stage, it's really difficult to change the fit of the socket. Carbon fiber is thermoset. The resin that we use is thermoset, meaning you can't heat it up and change its shape. Once it's made, it's made. And the way that we do this is we take this plaster cast that we fill from the test socket then, so we have a second plaster cast, and we'll build the socket around it. So we'll put layer upon layer upon layer of carbon fiber on it, and then stream some resin through it under a vacuum system. And then we assemble it all together, and the patient comes back and we fit them with the final prosthesis. The best rule of thumb for us is make it as strong as you can. So that's one area that we could really improve in the field of prosthetics, is that really finding the good balance between over-engineering, safety, and strength for our prosthetic sockets.